Hello everyone. Today we are going to do some practice problems involving the oxidation reactions of alkenes. Oxidation reactions involving alkenes can be used to actually identify the position of a double bond in an alkene, or it could be used to produce a new functional group such as an aldehyde or an alcohol, carboxylic acid. So let's have a look at a few problems. This first problem asks us to identify A, B, and C from the products of these different reactions. So our first one is potassium permanganate reacting with some alkene under heat and being acidified at the end. Okay, so one thing to note, we only get one product. Okay, the presence of one product indicates that this must be a symmetrical molecule. Okay, KMnO4, hot KMnO4, cleaves the double bond, producing two products. So anytime we only produce one product, it must be a symmetrical molecule. We're actually making two molecules of a single product. Okay, so what I like to do first is to just kind of work backwards. Okay? Working backwards, I know that this OH group originally would have been a hydrogen. Okay, before it was oxidized. I also know that this O originally would have been the other half of a double bond. In other words, it would have been a carbon. Okay, so what I'm going to do is I'm just going to copy this molecule. Okay, and if I didn't have a computer, I would simply redraw it. I'm going to copy it without those two oxidized features. And I'm just leaving right here. I know this is where the double bond was cleaved. Okay, so the other half of this double bond, knowing that this molecule is symmetrical, should be an identical molecule to this guy. So I just don't like to always keep track of my number of carbons. Here I have 5 carbons, so the other half of the molecule should have 5 carbons as well. Again, use my technology here. If this is the other half of the molecule, should be able to rotate it and just kind of put that in place. Oh. All right. Okay, so we can kind of just see if that's where the double bond was cleaved, this would have been our original molecule. I like to draw it a little neater after I figured out my final molecule, but counting up the carbons, this comes out to be 10 carbon with a double bond between carbon 5 and 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is going to be some kind of decane. Double bond in the middle. 1, 2, 3, 4, 5. Okay, so I've got 5 decene. Whether I have it drawn as cis or trans doesn't really matter. Okay. The next one is an ozonolysis reaction. We see ozone in liquid nitrogen, or ozone being cooled by liquid nitrogen. This would happen in a nonpolar solvent like CCl4, followed up by dimethyl sulfide. Okay, let's see. Ozonolysis cleaves the double bond and oxidizes it with an oxygen, forming a ketone or an aldehyde. In this case, it was an aldehyde. But again, I'm just going to follow the exact same pattern I did before. This produced only one product, which means it must have been a symmetrical molecule. Two identical halves, identical attached at this double bond. Okay, so I'm going to, again, rotate it, can. You know what, easier probably just to draw it again. Okay, so here would be my other half of the double bond. Okay, and that was the double bond that was cleaved by the ozonolysis. Just drawing this to make it a little cleaner. And I always like to double count my carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Okay, so just double check and make sure I didn't lose anything when transferring to a line structure. Okay. Lastly, we've got another product. Again, only one product. Makes it look like this is a symmetrical molecule. But this one's a little bit more interesting because it has two oxidized groups, indicating that this molecule was oxidized at two locations that are still attached to each other. Okay, so following the same pattern as before, I know that these OHs, they're not going to be in my final molecule, nor will these O's. And I know that these are going to be bonded to each other. Okay, so what's that going to look like if I redraw this molecule with those two double bonded carbons attached to each other? It is going to be a ring. So I'm going to take that out just to make it a little cleaner. The number of carbon in the ring is 1, 2, 3, 4, 5, 6, with the first and 6th carbon bonded to each other. 1, 2, 3, 4, 5, 6. Okay, and my carbon 1 and 2, or sorry, 1 and 6 are bonded to each other by a double bond. Okay, I get cyclohexene. Right? This is a ring structure. That's typical whenever you see a single product that has two oxidized carbons on it. In this case, the first and the last carbon. Okay. So we're going to try one more. This one's a little trickier because it has two steps. The first step asks what happens when we react it with H2SO4. Right? Remember, H2SO4 can do a couple things. It is used to dehydrate molecules of alcohols, which is what it's going to do in this case. It can also be used as a catalyst in hydration reactions, but if that were the case, I would have seen H2O as a reactant as well. So here it's a dehydration reaction. It's going to dehydrate one of the neighboring carbons to this OH, okay, and along with the OH group. Markovnikov's rule says that the double bond that forms as a result of this reaction will be between the most substituted carbon. So when I can choose between, say, carbons A, carbon B, A is more substituted. Okay, so I'm going to expect that double bond to form between carbon A and the OH carbon. Here, though, I also have to take into account stereochemistry. The hydrogen that's eliminated in a reaction like this is the one that is anti-periplanar to the OH group. Okay, so if this methyl group is up, the hydrogen there is going to be down. That is anti-periplanar to the OH. It can be eliminated. So it's worthwhile to check that because if it didn't have that hydrogen, A wouldn't have been an option for elimination. Okay, I'm just going to draw my product of the first step. Okay, this is now a planar bond around that carbon because it's trigonoplanar, only has 3 bonds, so I don't need to draw the wedge anymore. The next step says AMNO4, hot with acid H+. Okay, so that's going to cleave this bond, resulting in a carbon, which is 6 carbons. It might help you to number them, just so that you can keep track of where they are. This would be my carbons, just so that you can see where they are. I see that on carbon 1, I have a methyl group, so I'm going to draw that. Okay, and 1 and 6 are where this new functional group is going to be. So previously, 1 and 6 were bonded to each other by this double bond, right? So before, this double bond was attached, and now it's broken. And what's going to go in its place? Well, KMNO4 is going to replace it with oxygens. Okay, so right now I have a ketone on carbon 1 and I have an aldehyde on carbon 6. Um, Aldehydes are further oxidized. The hydrogen bonded to there is going to get oxidized to an OH. Okay, so any carbon, any hydrogens bonded to the carbon in the alkene double bond is going to get oxidized. All right, so we end up with this molecule that has a ketone and a carboxylic acid. Okay, so again, hopefully you can use these as practice for seeing how a reaction like hot acidified KMNO4 can be used to identify the original substrate just by looking at the products, in addition to predicting the products if you know the substrate. Okay, if you have any questions, please let me know via email or Google Classroom. Have a good one.